Good. Thank you very much. Yeah. So, thanks for staying and thanks for coming to this talk. So, I'm going to talk a little bit about something we've done with repurposed OCP hardware up in the north of Sweden in various different ways. So, from air to liquid, and some results that we have from that. Myself, my name is John Summers. Some of you probably know me. I'm the scientific lead in data centers at the Research Institutes of Sweden, and we have this cool environment up in the, cool in both senses of the word, up in the north of Sweden, where we have 1,000 square meters of lab space where we can do a lot of tests, and we've interacted and collaborated with a lot of different organizations that are providing, supporting the data center industry. So I put this under the cooling environments track, or sustainability cooling environments, because it was notionally dealing with the heat, here dealing with the thermal management of OCP equipment, but also the fact that we were repurposing the hardware. And, So basically, I'm going to introduce the repurposed server that we've used in a number of different situations. We've used it in direct fresh air. There's a lot of cold, fresh air up in the north of Sweden that we can take advantage of. We devised this holistic cooling control, which I want to explain a little bit about as well, which is synchronizing the cooling arrangements between the servers and the coolers. And this was actually a data center that we built out in Boden, which was 30 kilometers west of Luleå, where we're stationed. It was made of wood, the data center, and it was a 500 kilowatt data center, and we had one of the pods was dedicated to OCP servers. And then we repurposed that inside our facility to try and develop this holistic cooling control. The OCP gear, the more modern OCP, is very interesting because you have the fan control interface. And it's funny, when I first talked about this 4 years ago, taking control of the server fans, people said, oh, yeah, it wouldn't do that. And now we've got this initiative with OpenBMC, is that you can actually write your own firmware, and it's interesting what you can do, yeah. So you can literally do some wonderful things, potentially. We did some work with the same server, but repurposed it with direct-to-chip liquid cooling, and there's a solution here that we worked with a company in Ireland called Nexalus, and I'll explain a little bit about what we did there. And we've also, I think it's probably well known that we have worked with Immersion as well, and we use an Immersion system, and we've put some of the OCP servers in an Immersion tank. We've run it for over a year. So I can actually tell you what the ISO PUE is, and I can actually tell you what the ISO ERF is of that solution, which I will do at one point. What is the server? Well, it's an old server, 2014. Leopard, it's nominally the Facebook Xeon motherboard version 3.1 there. There's the link you can get to. So it looks very familiar. Two CPUs, they're E5 2678 processors, version 3. And peak 120 watts each. The RAM, we had 256 gigabytes of RAM, so the RAM was about 120 watts. So the server, without anything else, is around about 400 watts peak. There's no power supply because it runs off a DC bus, so the power supply is dealt with separately, unlike the pizza box servers. So we put this in an air-cooled environment. So this is a test data center that we developed, and what you see there are the two brown boxes. There are essentially the climate boxes, and they sit on front of two direct fresh air coolers. So what we do is we supply the air temperature which is the outside temperature, not pressurized or under-pressurized because it's supposed to be atmospheric pressure, but we can define a temperature, and then we can supply that to the data center, which had 360 of the OCP servers. You may ask the question, how does a research institute get hold of 360 OCP servers? Well, we have a friendly neighbor up there in Luleå, the large Facebook data center, Meta data center. A lot of this research that we did was supported by the European Union under the Boden Type Data Center project, and the grant number is at the bottom there in that slide. So basically we had two what they call fresh air coolers, CRECs, which supply air to the cold aisle. It's a contained hot aisle. And the idea here is that we took control of all the server fans. So each server has 2 fans. We had 360 of them, so we were taking control of 720 fans in the servers, but we had 2 supply fans from the coolers. And what we wanted to do is we wanted to slow everything down. So slow the speed of the fans down and look at the performance of the IT while we did that. So there's a control system on the cooling units, the direct fresh air units. They're basically ventilators. They came from the UK, one of the partners in the project who sold them and has sold a lot to the north of Sweden because it's easy to do cooling in the north of Sweden with all the direct fresh air systems that you can use. So essentially the control system allows us to control the fans, but it can consume water, so you can use what's called water economization. So it has 2 wet pads, and you can pass the air over the wet pads, and you can drop the temperature. In fact, in the north of Sweden, you use more water in the winter than you do in the summer. The reason is that you need to humidify in the winter. Because the air is recirculated in the data center a lot, and the humidity drops to around 3 to 5%. It's not a problem, really, to be honest, unless you're going into the data center and touching surfaces, and then it can be a problem. There's a control system on the servers, which manages the fan. So basically, the idea is to allow a real-time data exchange between the server and the coolers to produce this holistic cooling control. Here are some results. So on the left there, you can see the IT workload. So we use a synthetic workload. So we pushed on a V-shaped workload. So it went up to 110 kilowatts from idle power of about 25 kilowatts. And then we put a large square wave on it to peak performance of 150 kilowatts. What you can see with the yellow line is the actual, and that's red on the right-hand side, is the power consumed by the coolers. So the coolers, this was using standard cooling control based on temperature. You can use it based on pressure. And so what it said, okay, well, it's getting hot, I need to speed up my fans. But then the workload disappeared, but the fans had already ramped up. So the holistic cooling control, which is on the far right there, is switching on holistic cooling control, where you match the speeds of the fans to supply the correct amount of air for what's required by the servers. You can see that the actual fans didn't ramp up. You didn't need to ramp the fans up if you do that. You can see what happens to the supply and return. The supply temperature is the blue line there. The supply temperature to the front of the servers is still the same. No problem. But that's one of the issues. So that's standard cooling, and that's holistic cooling control. So that was one experiment that we managed to do. We have built a wind tunnel, and I don't know if anybody went to see the talk by Interact Tech Buyer. They have run a wind tunnel. Actually, one of my PhD students works with them. And we built a wind tunnel in the north. This is the 3rd wind tunnel that we've built. And the basic idea here is you have a very highly controlled environment, so you can actually put a series of servers in there, and you can test them. And we put a humidifier in the loop there as well, so we could control the temperature to the front of the servers, we can control the pressure drop across the server, and we can control the humidity. There's a lot of things you can do with that. But one of the things that we did find with these servers, and this is really interesting, is that the red dotted line, which is to be read on the right axis, is actually the power consumption of an individual server. At 8% workload is the top one, 50% the middle one, and 100% the bottom. And the other 2 curves, the solid red curve is the dotted red curve is the overall power consumption. The solid red curve is actually the power from the thermal power, so discounting the fans in the servers. Whereas the black dotted line is the fans in the servers. So what we were able to do, because we had control of the fans, was we could say, I want the CPU to operate at 60 degrees all the time. irrespective of whether it's running at 8%, 50%, or 100%. And because we can do that, we could then measure the power draw of the server and the power consumption of the fans. And then that's one server, but then when you put all the servers into a data center on the right there, you can see that actually, once you bring the cooling system into control, the black curve is actually much bigger. So the fans, running the fans at high speed, that's the whole reason why we want to slow things down. And so you can see there's a sweet spot of operation. So where the red curve drops, and that's the temperature that you should really operate your data center. But the sweet spot moves as the workload changes. So if we had some way of controlling the BIOS so that we could change the temperature of operation of the CPU, so you're always at the sweet spot, then that's what the BIOS should be doing. These were the actual red dot on there is actually what is actually done by the BIOS if we didn't take control of the fan. So we actually spent a lot of time and money finding out that Facebook actually does a good job, because the servers are running at quite a good sweet spot. Here's an example of two workloads, exactly the same workload, okay, run over 120 hours on the data center, one where we allow the BIOS to set the temperature of the CPU, so the fans are regulated by the CPU, and the other one is where we said, I want the CPU to be 70 degrees all the time. So you can see with the control of all of the fans in the data center, we were able to maintain a temperature of 70 degrees on the CPU, irrespective of the workload. So it's the same workload played twice for 120 minutes, except one is with control of the fans, and the other one is just left to the BIOS. And the great thing about that, why do you do that? Well, you maintain a high delta T across your IT all the time. And it comes back to reusing the heat here. If you've got a high delta T, you've got a high temperature in the hot aisle, you've got a better access to it. And you can see that with these two traces. The top trace there is with no control, and the bottom trace is with control. And there's a constant delta T between the hot and the cold aisle as the workload changes. I mean, the reason there's fluctuations at the temperature is because we're using outside air temperature, so there's a bit of fluctuation in that. Over 120 hours is 5 days, so the weather does change outside in 5 days. So we took these repurposed servers and we said, okay, let's throw away those heat sinks, those very cheap heat sinks with a couple of heat pipes in them, aluminium, brazed aluminium, and let's put on some water blocks or the cold plates, and we're using these cold plates supplied by Nexilus. And the interesting thing is that the airflow on the server goes that way, but what they did is because when you're only concentrating on the microprocessors, you still have to cool other parts of the IT. So the airflow there, you can see there's an airflow and a water flow in opposite directions in the setup. We saw the same kind of behavior. Again, we saw the fact that there is a sweet spot of operation with, you can see as we dialed in. And how did we dial in the temperature of the CPU this time? We had control of the pump that's pumping the coolant to the heads. So we can dial in a temperature, and it maintains that temperature of the CPU. And then we could read off the power consumed. And what you can see, the difference between 30 degrees, 40 degrees, and 50 degrees, this is actually the temperature of supply to the IT. You can see, obviously, when you're running at 50 degrees, you can't ask the CPU to run at 50 degrees as well, because 50-degree water on and asking for 50 degrees from the CPU is not physically possible. The interesting thing is actually the heat of the return coolant, because that's what you can get access to and use. And in all cases, 8%, 30%, and 75% workloads that we operated with, we were able to get over 60 degrees. So with direct-to-chip, you can safely say that you can get reuse the heat at 60 degrees, I think. And the workload, if the workload's not heavy, you can just run things slower and pick up the heat. Then we threw all these servers into an immersion system, and some of you may recognize which immersion system that is. But here you have 2 power shelves. So there's 2 power shelves sitting in, And there's 2 bus bars at the bottom. So there's 2 12-volt bus bars at the bottom of the tank, and we've got 54 of these OCP servers in the tank, and 27 on one bus bar and 27 on the other. And so the power is converted in the tank and then supplied to the 54 servers. So what can I say? Well, we have a very good monitoring system. So we use a lot of open source software. We use Zabbix, Logstash, NiFi, Kafka, KairosDB in a daisy chain of open source software, and then we look at everything in Grafana at the end. And all of our test rigs, this is only one of the test rigs that we've been running with, are all connected to the same data collection system. And if we can measure it, if we've got a sensor, we put a sensor in. If we've got the sensor data, we go for it. So IPMI data, redfish data, we get all access to all the server data. And this doesn't really show much, but it shows a workload on the data center there, because this 54 servers at a maximum peak of 400 watts. You're around about 22 kilowatts in the tank, but we're running with about a 50% workload there, but it's fluctuating. I can't tell you much more about this, but it actually isn't running on electricity. It's running on biogas. That's another story. But I have done because I keep getting up and talking about PUE and ERF, I thought I changed the slide at the last minute. I thought, what is the ISO PUE of this? It's actually 1.31. It's an ISO PUE because it's annualized. It's over 1 year. And it's PUE 1 because it's actually the power that's measured at the UPS, or we don't have a UPS, but at the point of delivery. And so 1.31 is quite high, right? But we are actually reusing the heat because the data center is connected with the fuel cells that are producing the power to the data center that are running off biogas. Is connected to the district heating. And we are supplying 60 to 65 degrees of heat to the heating network. So the ERF is annualized over 1 year, it's 0.09. So this energy reuse effectiveness, which is not an ISO metric, is the PUE multiplied by 1 minus ERF, so that would be 1.19. And so if there was a mandatory requirement to be less than 1.2, it would make it. But 1.31 PUE wouldn't make it. And that's the point I was trying to make. It's about heat reuse. So the call to action really is, and I haven't said much about the performance of the IT. I apologize, there's so little I can say in 20 minutes, and I talk a lot. So, but really, it's the reuse of the IT. The IT still, even 2014, it still has a lot of capability in it. And you can repurpose it for direct-to-chip. You can repurpose it for immersion. You can put it in an air-cooled environment. It doesn't matter, really. But I really think, from the sustainability working group, that we should look at the metrics around repurposing IT. The other thing that's interesting here is that in an air-cooled environment, the Open BMC initiative, and I know some servers you can purchase now have this Open BMC, so you can write your own firmware to control the fans. And perhaps that, alignment with that would be very useful. But on that note, I will finish with some time for questions. Yeah. Sorry, that was very quick. Don't leave now, Holly.
Sorry, John.
Thanks a lot, yeah. Any questions, or have I answered everything in my... No? Go on, Jerome, yeah, surely you've got something to say, yeah.
Yes, typically, I think the immersion and all the liquid cooling is advertised with a low PUE. How do you end up at 1.3?
Good question. Yeah, you're very observant, right? So first of all, the immersion tank has an 800 watt pump, and it comes on. Basically, you set the target temperature of the tank. So the tank has a target temperature of, and we maintain it at 50 degrees. 55 is a bit tricky. 50 degrees in the immersion tank, and what happens is the temperature in the tank goes up, and when it gets into the deadband region of the set point, it switches the pump on. Now the pump is 800 watts, but the IT is only consuming 14, 15 kilowatts, so 800 watts, but it's intermittent. The other thing is it's in a container outside in minus 25. So there's a small heat pump inside the container as well. There isn't enough heat generated by the immersion system to keep everything else at the right temperature. So the heat pump is coming on intermittently. The pump itself is coming on intermittently to reject the heat. And so if you look at the trace, the time history of the 1 year of operation, it's very noisy, but unfortunately that's the data. The kilowatt hours, the megawatt hours consumed of the whole container divided by the megawatt hours consumed by the IT only, and that is no fans in the IT, that's just purely the microelectronics. So that's the other thing, is that because the fans are usually in the PUE, it makes the PUE look better in an air-cooled environment. But you're still in a liquid-cooled environment, I've removed all the fans. So there were 108 fans that I've just thrown away.
Yeah, you put it into a pump. So
yeah, you're putting it into the pump. Yeah, so, yeah.
But actually what you're now saying is that in a hotter environment, it would run at a better PUE because you would be able to get rid of the heat pump.
Yes, you would, yeah. Well, the question is whether we should have had the heat pump, really, whether we should have run, because actually, the condensation is a problem. So you can run the container minus 25 outside. You can let the container go to sub-zero inside. The water glycol loop will not freeze. The hydrocarbon will not freeze. But the problem is you've got a lot of cold surfaces, so you get a lot of condensation. But so we never chanced that. We wanted to reduce the condensation. So it's a dew point control issue, not anything to do with the heat, if you see what I mean. Yeah.
In a hotter country, you will have a lower PUE, but then the heat reuse might not be as necessary as you mentioned earlier.
Yeah, that's true. So the heat reuse is yeah. But the data, you can't argue with the data. That is the data we collected. Yeah, I mean the sensors you could say are not that. Maybe they have a level of accuracy, but it's small in terms of the meters that we're using. We are using Janitza meters on everything, so they have Ethernet. They're connected to the data collection system. Yeah.
It won't be in the measurement.
No, it's not in the measurement area. No.
This model is plausible. One of the other presentations they were saying, I think it's pretty standard that most processors are only running at about 25% capacity. Do you think it's plausible to start reusing older technology in some kind of an immersive scenario so that we run hotter, so that we actually expand the refit?
Yeah. I believe that is not. That's a good point. Why wouldn't you do that? I mean, I think the thing today is that the energy consumption of the IT and the value of that, the work that they can do is they've still got quite a lot of life left in them, and so why not throw them in an immersion? And in actual fact, the thing about immersion is, compared to direct-to-chip or air-cooled, is you don't get the same kind of thermal shocking. So if you turn something off or you lose your cooling system for a while, for example, you see a massive change in temperature. In an immersion tank, because you have so much thermal inertia, they don't see a big change in temperature, hardly at all. So it protects the IT, if you like, being in an immersion system. But I tell you what, it is messy, pulling servers in and out. It's not easy to maintain, so easy to maintain. That's the one small drawback. But the other interesting thing is that you can put we only have one CDU in the tank, so it's connected to one water circuit. But you can put two cooling distribution units in the tank, and they can be connected to different cooling loops, and so you're concurrently maintainable. Difficult to do with direct-to-chip.
John, how do you compare different technologies then? Because if that was air-cooled, the PUE is different, but you consume a completely different amount of energy. So how do we get around this problem where you're getting measured on a metric that doesn't actually give you the value of the energy consumed?
You have to go for the source, don't you? You have to go for the IT. You know, what's the IT doing and how much energy has it consumed to do what it's doing? And this boils down to the biggest problem we have in this industry. We don't have a good energy efficiency metric. And you know, PUE will always will only give you one fraction of the story. ERF gives you another fraction of the story. But do all the metrics that we have give you the full picture? And I would say no. Because even the ITEU, and Gerard is shaking his head there, I can see you, the ITEU and the ITEE are just not, are part of the, they solve part of it, but they don't give you the full picture, yeah, so there's still a long way to go with metrics, yeah, I think, but it's a good question, Mark, yeah, it's Peter, yes, yeah, he's, yeah, he didn't include water, did he? He's not here. Is he here? It doesn't include. Does it include water but it includes renewable energy, I think, and reuse of energy as well. I better get off the stage, shouldn't I? Because there's somebody else there. But thanks for interaction, guys. Thanks. Yeah.